All right. So this is a little video about half-life. Okay? Half-life is the amount of time for half of a sample to react, and this works in nuclear physics. It's also a term that we use in chemistry, just like how long does it take half of the material to react. So what time zero, I should have, oops, what's going on here? Time zero, I should have all the sample here. But after one half-life, half of it should have reacted, and this half, the red half, remains. And after another half-life, half of that would still remain. And after another half-life, I would only have that much. So it's not after two half-lives it would all be gone. It's all relative to how much you started with. So some things have a very short half-life. And there are all sorts of isotopes that have a really small half-life, but some have a very large half-life. And this is the problem. This is nuclear reactor waste often has a really, really large half-life. An application of half-life is carbon dating, something I'm guessing many of you have heard about. When we're alive, we breathe, we eat, we go to the bathroom, yes? So the amount of radioactive carbon in our bodies is relatively constant, yes? But when we die, all of this stuff stops. And so the amount of radioactive carbon we have in our bodies starts to go down, and it goes down according to this graph right here. You know, this graph, I guess there's a limit to how accurate carbon dating would be. This graph is dropping off. I personally, after like in this area right here, yes, I'm not sure how accurate it becomes because for here, there's a large drop down, yes, but here things really start to change. For a really small amount of time, we get a bigger change. So we have to just be careful about using carbon to date super old things. When we are trying to date super old things, they turn to other ones, other radioactive elements. They look at Mg, they look at Al. There's other things they can look at with longer half-lives in carbon. Let's take a look at the math. Okay. This is the formula. Unsurprisingly, a formula for half-life has a half in it, a fraction. A0 is the amount that I start with. A is the amount that I have at any time t. These two things need to have the same units. And the same thing up here in this exponent, I have t divided by h, and t is the time and h is the half-life, and these have to have the same units if we're going to successfully solve problems. Now, this formula works for A or A0. When I have to solve for T or H, I start to have a bit of a problem because T and H are in the exponent, and like, how do I get them out? Well, how do I get them out? I'll just derive it really quick. I'm going to use logarithms. I'm going to bring the A0 over to beside the A, and it's going to go underneath. So I get A over A0 is 1/2 t divided by, oops, that's a t divided by h. And then I'm going to take the log or ln, they're the same thing, just different base. It's a button on your calculator, ln. Log works the same, but I like to use ln. I'm going to take the ln of both sides. So the ln of a over a0 is equal to the ln of 1/2 t divided by h. Now, it just so happens, why we're doing this is that there's a law of logarithms that says when I'm taking the log of something that has an exponent, I can actually take this exponent and put it out here, and they're equal. So I get ln of a over a naught is equal to t over h ln of 1/2. And now, using this trick of logarithms, the t and the h are no longer stuck up here in the exponent. They're out where I can naturally solve for them. So if I want t or h, I should use this formula. And if I want a or a0, I should be using this formula. And I will do 2 questions, one with each. Okay. Here's the first one. This thing has a half-life of 3 days. And we're going to start with that many milligrams. And it's telling me the time is 10 days. And it's asking me how much will I have. So I'm going to write the formula. Oops, that should not be there. Let's start that again. A equals A0 1/2 T over H. And I'm going to plug in 1200 times 1/2, and then this is going to be 10 divided by 3. Now, what I would do on my calculator is I would punch in 0.5, and then I would do the little exponent button, little upside down triangle, and then I would hit a bracket, and then I would do 10 divided by 3, and then I'd end bracket and I'd hit enter. And then I would get something on my calculator, and I would multiply that by 1200. And when I do all that, I would get 199 milligrams. So you should make sure that you can use your calculator to get 199. And if you can't, ask me, ask around. All right, one more. So I've got the half-life, it's telling me is 7370 years. How long? It looks like I'm solving for t, and I know that if A0 is 1, A is going to be 0.73 because it's saying that I'm only going to have 73% left. So this is a little trick. Anytime you see a question like that, let your original amount be 1 and then let A be 0.73. So I'm going to use this second formula. Ln of A over A0 equals T over H ln of 1/2. And I'm going to plug in what I know. So this is ln of 0.73 over 1 is T over 7370 ln of 1/2. So I would work on my calculator. I would work this, the ln, I would do the ln of 0.73. Yes. Divided by 1. Then I'd hit enter. I'd multiply that by 7370 because I'm going to swing the 7370 over here. And then I would divide it by the ln of 0.5 and I'd hit enter. And when you do all that, you get a time of 3,346. And the units have to be the same as H. So it would be years. So there's 2 examples using each of the formulas. So let me know if you have any questions. And that's it.